Welcome to NASA eClips Earth Day Marathon. Today, we'll be exploring the Earth sphere by sphere, starting with the geosphere. The geosphere is the solid rock our world is made of. Before we begin, let's get an introduction to all of Earth's spheres and how they relate to each other.
Hi, I'm Michelle for NASA eClips, and today I'm at the Virginia Living Museum in Newport News, Virginia. Today I'll be talking with some NASA scientists to learn more about how scientists gather information about Earth systems. I'm here with Jessica Taylor from NASA Langley Research Center. Jessica is an atmospheric scientist.
Hi, Michelle. It's nice to meet you.
It's nice to meet you too.
I understand that you want to learn more about how NASA scientists gather information about our Earth.
That's right. For my science class, I learned that Earth is a part of one big system, but it also is a part of some smaller subsystems. But I'm not quite sure how all of that works together.
Well, why don't we go inside and go to the cypress swamp, and I can show you a little more about how these Earth systems interact. As you can see, the Earth really is a complex system. Changes in one part of the subsystem can impact the whole planet. Scientists study the Earth system by looking at multiple spheres. The water here is an example of the hydrosphere. The air that we breathe is an example of the atmosphere. The land that you see here, that's an example of the lithosphere. And all of these animals, the turtles, the fish, and the ducks, they're all part of the biosphere, living things. And then there's the cryosphere, ice. We can't see that here because we're in Virginia, and it just doesn't get cold enough here. Scientists keep an eye on these systems to make sure they're functioning as we expect. While scientists look at changes right here at our Earth's surface, NASA also uses satellites, with instruments looking back down at Earth from space. And we use these satellites to collect data for long-term global perspective.
So what kind of tools do you use to look at those changes?
Well, let's find out more by talking with a friend of mine, Dr. Stephen Pawson. He's at NASA's Goddard Space Flight Center. So let's come right over here, and we can call Dr. Pawson directly.
Hi, Dr. Pawson. Jessica and I have already talked about Earth systems, but I don't understand how these systems affect climate or how NASA can track that.
Yes, I'm very happy to talk about that. First, what we know about climate is that it includes not only the temperature of Earth, but also a lot of other things, such as the cycles of carbon and water. Now, what does NASA do? Because NASA builds satellites that can orbit Earth, it means we can see all places from space. This gives us a much bigger view that we can see from the surface alone. So the instruments on NASA's satellites help us see the complete Earth and also measure different parts of the climate system.
So Stephen, can you explain to Michelle a little more about the tools that are used to gather this kind of data? And then once NASA has the data, how is that data analyzed and visualized?
So I think what's very interesting is that usually when we're measuring from space, we're actually measuring the light that's coming into the satellite, whether that's light in the visible spectrum that we can see, or whether it's infrared or ultraviolet light that we can't see, but it's still part of the electromagnetic spectrum. And to make real use of these data, we have to be able to deduce the quantities that we're interested in. So we know that if we're looking for ice, then if there's a lot of ice, more light will be reflected, and if there's not much ice, it won't be reflected. So in a way, that's a relatively straightforward measurement. We can detect if there is ice there or not. But typically, if we're trying to deduce the temperature of the Earth from space, then we're looking at a different part of the spectrum, and we have to be able to separate impacts of temperature from water vapor and from other gases in the atmosphere, and do what we call a retrieval of that information. And a retrieval is really using a lot of complex physical models to try to understand what it is that we're observing and what's causing the change in the light that we're measuring. Typically, the physical models are mathematical equations, but what we actually do is code them to run on a computer. Instead of treating just one column of the atmosphere, we're looking at a grid over the entire Earth of points, and that includes the atmosphere, the land, and the ocean. And when we know what the state is at any one time, we can run those models forward in time using very, very powerful computers. And from those, we can deduce what is going to happen in 1 day or 2 days. For instance, we can make weather forecasts, or we can run climate projections, which are running up to about 100 years ahead. Using this technique, we're able to deduce a lot of information about the surface of Earth and the atmosphere, and even the surface layer of land and oceans from space.
Thank you so much to Dr. Stephen Pawson and Jessica Taylor. Want to find out more about Earth systems and the work being done by NASA and other scientists? Go to this website. That's all for now. I'm Michelle, and I'll see you next time on NASA eClips.
Now that we know more about all the spheres, let's take a closer look at the geosphere, starting with the rock cycle.
You know, Globey, here on Earth we have three basic types of rocks: igneous, sedimentary, and metamorphic rocks. Scientists classify these rocks by the way they were made. Igneous rocks are formed when lava from a volcano cools and hardens.
Igneous rocks are also formed when magma cools below Earth's surface.
Sedimentary rocks are formed when the elements wear rocks down into tiny particles of dust, sand, and soil. Wind and water help move these particles around and deposit them into layers. As time passes, these layers are cemented together and harden into new rocks. Metamorphic rocks form when sedimentary or igneous rocks change after being exposed to extreme heat or pressure without melting. As conditions on Earth change, rocks may change from one type to another. Sedimentary rocks can change into metamorphic rocks, or, if they melt, into igneous rocks. Igneous rocks can change into sedimentary or metamorphic rocks, and metamorphic rocks can change into sedimentary or igneous rocks. Scientists call these changes the rock cycle. But NASA scientists want to study rocks from other places, like the Moon and Mars as well. They want to see if other rocks are like the rocks found here on Earth. By studying rocks from the Moon or Mars, scientists can learn a lot about how the land was formed and how it has changed over time. The history of rocks. They can tell how the geologic history of another planet compares to the geologic history of Earth. During the Apollo missions to the Moon 40 years ago, astronauts brought back dozens of rock samples from the Moon's surface. Today, scientists from all over the world have a chance to study these lunar rocks. And by studying the rocks, scientists have discovered that the rocks on the Moon can be classified into three basic types too. The first is lunar basalt. This type of moon rock is similar to volcanic lava found on Earth. It starts on the Moon in a lava state and then cools to form a hard rock.
The second type of moon rock is called a northocite, which forms from the cooling of a large ocean of magma shortly after the Moon was formed. Lunar breccia is the third type of rock. Light areas of the breccias are either pieces of a northocite or unmelted rock. The dark areas are either basalt or melted rock from the meteoroids hitting the surface.
Thanks to the lunar samples brought back by NASA astronauts, scientists finally know what the Moon is made of. No, Globey, it's not cheese. But scientists aren't the only ones who get to view the lunar samples. The Lunar Sample Laboratory Facility at NASA's Johnson Space Center also lends moon rocks out to educators and museums around the world. Some of the samples have been preserved in round discs of clear lucite. People who have had special training take those samples to classrooms and museums so many other people can see what these special lunar rocks look like. A few museums have their own moon rock on display, so you can visit a museum and see a real moon rock in person. The lunar rock samples brought back from the Moon 40 years ago still provide meaningful data to scientists all over the world. They continue to teach us how the rock cycle on the Moon is similar in many ways to how rocks change on Earth, or even other planets. So now you know how rocks grow and change beneath our feet, thanks to the rock cycle.
The next step to understanding the rock cycle is creating a tasty, hands-on model. Follow along with Elise to learn how.
Hi, my name is Elise Mouton, and today we will be doing a fun Earth Day craft that will help to demonstrate the rock cycle. In order to do this activity, you will need a hairdryer, aluminum foil, scissors, and taffy. You can use Starburst, Haichu, or Laffy Taffy for this activity. However, you should make sure that you have a couple different colors. We will start by taking the Laffy Taffy out of the wrapper. The taffy right now can be represented as an igneous rock. Now we will take our igneous rock and cut it into small pieces. Cutting up the taffy represents the weathering of the igneous rock. Because of the weathering, the taffy now represents a sediment. Now we will go and mold all of the pieces together. This is the compaction and cementation that the sediments go through to become a sedimentary rock. Now we have a sedimentary rock. Now that we have a sedimentary rock, we are going to apply some more pressure and mix the taffy together some more. This is helping to show the heat and the pressure that the sedimentary rock goes through to become a metamorphic rock. Now that we have a metamorphic rock, we are going to take some aluminum foil and mold it into a plate-like shape. Now that we have our aluminum foil plate, we will take our metamorphic rock and place it inside of it. Next, we will go and we will grab our blow dryer and turn it on to hot mode, and we will blow dry the taffy. Once it has become a liquid, we can stir up the magma. Now that it has been thoroughly stirred, we will let it cool. Once it has fully cooled down, it will then be an igneous rock once again. This is the full cycle for the rock cycle. Thank you for watching and have a great Earth Day.
Now that we understand the rock cycle, let's zoom out to learn how NASA studies rocks and other forms of land cover.
My land cover career really started in 2002 with biggest wildfire in Oregon's history, and that was the Biscuit wildfire. I, at the time, was doing botany surveys and looking for rare plants or rare mushrooms, and so I was spending a lot of time out on the forest looking at and taking photos and doing the documentation that a scientist or a land manager does. When that fire happened, it changed everything, because we all had to react to this fire that was burning up some of the places that I'd literally been the day before. And it was mapping what was there and what was under threat, but it was also mapping the effects of the fire. We needed to find a way to look across 500,000 acres. And the only way that we could really do that was satellite data. If we can't get out and actually measure every single thing, what are we missing? And that's where citizen scientists can actually come in and really help traditional scientists to better understand what is happening around them, but also fill in these gaps.
The Global Learning and Observations to Benefit the Environment program is an international science and education program. It provides students and the public with the opportunity to participate in data collection and the scientific process. The Globe Observer app is one of these opportunities, allowing citizen scientists and students to take land cover observations around the world and submit them to a larger database. But what exactly is land cover? Dr. Eric Brown de Colston of NASA's Goddard Space Flight Center explains.
Land cover is really the basic form of the landscape that we have around us. So whether it's a forest or a desert, but it's really one of the components of the landscape that we can study from space.
Peter Nelson is a scientist who uses land cover imagery in his research.
I am a remote sensing scientist who studies land cover across the globe. I use satellite imagery to make maps of land cover and try to quantify what covers the Earth. Sometimes a satellite can't see what's happening underneath a tree canopy or what's happening underneath cloud cover. And so we really need people to go out there and to take these photos, to do these observations, to help fill in where a satellite can't actually make some observations.
Just like any digital photograph, land cover images are made up of a series of pixels to show what covers the Earth. A pixel, or picture elements, is the smallest unit of a digital image. When combined with thousands of other pixels, a picture is formed. Each pixel color shown represents a land cover type. It's from these pixels where ground verification or ground truthing come into play. You see, depending on what satellite is taking images, a pixel can cover roughly an area of 30 to 500 meters squared. For imagery captured by Landsat, a pixel is 30 meters squared, or about the size of a baseball diamond. However, part of that pixel showing forest might actually be water, or shrubs. By taking land cover observations, citizen scientists can help answer these questions when it comes to land cover maps. So, why are these land cover observations so important? Why are they taken in the first place?
We also are looking at how these components are changing over time. So deforestation in the Amazon or across the world, how are cities expanding? A lot of different things to study, and really the view from space is the way that we do it here at NASA. We have big supercomputers that simulate the physics of the atmosphere and the land, the interaction between the Earth systems. It's important to have that, that land cover map. It sets certain parameters. Those models can actually be used to look at current day conditions and weather. So based on these current conditions, what might the Earth look like 50 or 100 years from now? There's an element of understanding, but then also being able to predict into the future, what that might be like, what these changes may mean for us.
Each point shown here represents a real-world measurement of environmental conditions. Scientists use computer models to fill in information where measurements may not exist. By verifying the satellite imagery and using the data for these models, scientists can predict changes in our environment more accurately. One of these scientists using land cover maps to track urbanization as part of her work is Dr. Amita Mehta of NASA's Goddard Space Flight Center.
So urbanization changes terrain as well as characteristics of the surface itself. And so impervious surface is what we look at when we are monitoring flooding. When there are, say, parking lots or cement and concrete surfaces, they increase. So previously, if it was a farmland or something which was not built, and if that is built now, that water previously that could go or percolate in the soil and in the ground now cannot go in, and it stays there. Monitoring helps you to plan for it. If you see land cover changing, even then you know that how water is going to flow in that region might change. If you have to send rescue out or you have to plan for relief activities, then if you know land cover, then you know where there might be help needed.
By using land cover maps and models that reflect changes over time, scientists can predict where flooding and other events may occur. With a changing climate, these predictions from models and land cover maps can help scientists better understand these changes and help communities prepare for them. But perhaps a more important reason as to why I take land cover observations is you get to participate in a community of scientists, citizen scientists, and students.
So it's a very important component that the citizen science and students of the GLOBE program and GLOBE Observer can contribute to is by really giving us the information on the ground of what they're seeing around them and in front of them. And we hope over time as well how maybe some of these things are changing, because those would be very valuable for science.
I saw the value of having information before a hazard happens, because once that fire went through an area, we can never recreate that data. This is all important for us to share and put together because that's how we understand Earth as a system. All of these things end up affecting where we live, why we live where we do, and why we make some of the choices that we do.
To learn more about Globe Observer, check out the website at observer.globe.gov and download the app to start taking your own observations today.
Here's an experiment you can try to learn how land cover affects all of us.
This is like the second time that this has happened this week. I wish I could just walk on concrete all the time so that this would never happen again. You know, that's not a bad idea. We just replaced all of this with concrete, I would never walk in mud again. I mean, it's not like it really matters, right?
Hold on. You can't do that. Land cover matters.
Wait, what do you mean? What even is land cover?
Land cover is defined as the physical material at the surface of the Earth. But why does it matter? And how can it impact communities? To learn more, let's try a simple experiment.
All you need are different samples of different land types, paint bins to hold them, some water, a measuring cup, and sprinkles are optional. You'll want to place your surface sample in the shallower end of the tray, like so. And then, in order to boost up the deeper end of the tray, you'll want to put a rock or a piece of wood under the shallower end to keep it stable. Here we have samples of concrete, gravel, sand, and sod. The sprinkles will represent the pollutants that rest on these surfaces. Now, let's see how it interacts with our simulated rainfall.
Gently pour 1/2 cup of water evenly over the surface samples. Take notes on how each surface sample interacts with the added water. Does the sample absorb it fully? Does all the water run off to the bottom of the tray? Or is it somewhere in between? What happened to our pollutants or sprinkles? Try this experiment and consider these questions. Does land cover matter? If so, can it affect communities? What types of land samples seem most beneficial for communities? Why? What about the most problematic?
There's one part of the geosphere I know you've heard about: volcanoes. Let's learn how NASA studies volcanoes on Earth and in space.
Earth is constantly changing the way it looks, and there's more happening beneath our feet than you might expect. Can you tell the difference between these two mountains? The difference is earth-shattering.
The difference between a mountain and a volcano is that volcanoes are formed from lava, whereas mountains are not necessarily formed from lava. Volcanism changes and shapes our planet by giving us new land masses, such as Hawaii, such as Iceland. And it also builds these tall, mountain-like structures on the surface of our planet. And in many cases, it actually helps to make the ground more fertile for planting of different types of crops.
Volcanoes are places on the Earth or other planets where molten material from the inside comes up and flows out or explodes out onto the surface. Volcanoes will form anywhere that the material from the inside can make its way to the surface. Sometimes the material will just shove its way up and make its own pathway. Other times it'll follow a fracture or a crack through the rocks at the surface.
Faults are just cracks in Earth's crust that form the boundaries for Earth's tectonic plates.
One of the things you can actually tell right away from looking at a volcano is if you look at its slope. If you just look at the volcano as a whole, it's just the height divided by the width. A shallow sloped volcano was one that was formed by magma that had a low viscosity, that was runny. And a steep sloped volcano is one that was formed by a magma that was sticky. When magma moves around, it has to push the rocks around. And one way that we can measure that is through the breaking of the rocks using seismometers.
Volcanoes play a role in how Earth looks today. But did you know that volcanoes are on other worlds in our solar system? You didn't? Well, that's not your fault.
Mars has volcanoes. Actually, the largest volcano in our solar system, Olympus Mons, is on Mars. Venus has volcanoes. Jupiter's moon Io has lots and lots of volcanoes, and there are hundreds of volcanoes on Io's surface, and they erupt daily.
Not all planetary bodies are made of rocks, and in fact, in the outer solar system, the majority of the bodies out there have an icy surface. And so through heating and other mechanisms, you can melt ice just like you can melt rocks.
And so when we have volcanism on these moons, instead of taking the form of hot rock or lava that erupts onto the surface, we have slush that erupts onto the surface. What we call this cold volcanism or this icy volcanism is cryovolcanism. If you have a planet that has a very smooth surface, then you know that volcanoes or cryovolcanoes have been active. You know that there's been some fluid, whether that be lava or when you're talking about icy volcanism, an icy lava or cryolava that's erupted onto the surface and it smoothed the surface out.
Cryovolcanoes? Cool. So there are different types of volcanoes, and they can be found all over our solar system. But how do we know this?
So the technology that's used to explore volcanoes that I use the most is basically data that comes back from robotic spacecraft. So NASA has sent spacecraft to many planets and moons. From these pictures, we're able to determine how tall these volcanoes are, how wide they are. These spacecraft also have instruments that tell us about the composition of those volcanoes. What we're able to do with that information is we're able to use then computer models and mathematical equations to try to figure out how these volcanoes formed, how runny the lava was that formed them.
Other ways that we can monitor volcanoes include paying attention to gases coming out of fractures around the volcanoes. A really big volcanic eruption can have global effects. Something big like Mount Pinatubo put so much ash into the air that it actually cooled the Earth off for a little while.
It's important to study volcanoes because they teach us a lot about the interior properties of planets and moons. So if we see volcanoes on the surface of a planet or a moon, we know at one time or another that the interior was warm enough to sustain that type of activity. When we think of our own planet Earth, volcanism has been very important. We have this very nice atmosphere that, full of nitrogen and oxygen that we breathe here. Early Earth's atmosphere was actually formed from gases that erupted from volcanoes.
It's important to study volcanoes no matter where they are. And thanks to NASA, we know more about volcanoes on our planet and in our solar system. Talk about explosive science. For Real World, I'm Michelle.
I love learning about volcanoes. Here's a tutorial you can try to create your very own volcano and study it like a scientist.
Hi everyone, this is Brandon from NASA's Jet Propulsion Laboratory, and what we're going to do today is create and map a volcano using baking soda, vinegar, and Play-Doh. Then we'll investigate what it's made up of, like we do with volcanoes on Earth and on other worlds. Let's begin by taking a small paper cup and cutting it such that this will represent our crater on our volcano. Add a small amount of baking soda to the crater, and then add vinegar to create an eruption. With each eruption, we'll deposit a lava layer onto our surface. This can be a piece of cardboard or a cooking tray. Lay down a layer of Play-Doh, either homemade or purchased, that will allow you to create this layered system. Try to be a good cartographer. Using a piece of scratch paper or graph paper if you have it, map out where this lava layering took place. You can repeat this 3 or 4 times to create a more complex volcano, each time laying down another layer and keeping good track of it on your map. So here's where the fun comes in. If possible, switch with someone else and challenge yourself to figure out what's under the surface of their volcano. This can be done by taking a simple plastic straw, cutting it into small pieces, and using it as a core sampler to see the lava layering that took place. From the core samples you collect, see if you can draw where the hidden lava layers are and figure out how big each one is and the order in which they were deposited. Compare your prediction to the known map that was created in the first step. For more details on this activity, visit this page or click the link in the description and check out the JPL Education website for more fun activities to try from home.
We learned that the geosphere is made up of soil, sediment, and rocks. All of these elements come together to create the Earth that we stand on every day. Before we hop into the next sphere, let's learn more about the NASA eClips team. Most of the videos seen during this marathon come from NASA eClips. Our team provides educators with videos, activities, and lessons to increase STEM literacy through the lens of NASA. A big part of eClips is our student-produced content. Our Spotlight Challenges encourage students to engage in experimentation and evidence collection, as well as develop their multimedia science communication skills. See other examples of Spotlight videos on our YouTube channel and learn more on our website, nasaeclips.arc.nasa.gov. Another thing that we rely on every day is water, and that brings us to the hydrosphere. The hydrosphere is made up of all of the water on the planet, whether that's in our clouds, our oceans, or frozen at the North Pole. Here's a video to introduce you to the most important part of the hydrosphere, our water cycle.
Water is all around us, and its importance to nearly every natural process on Earth cannot be underestimated. It is the only compound that can be found naturally as a liquid, gas, and solid. The process by which water moves around the Earth, from the oceans to the atmosphere to the land and back to the ocean, is called the water cycle. Water regulates climate, storing heat during the day and releasing it at night, and carries heat from the tropics to the poles by sea and by air. Let's follow a single molecule of water beginning in the ocean through the paths it might take before eventually winding up right where it started, back in the big blue sea. The fuel for this journey will be provided by our planet's prime energy source, the sun. During the day, the sun heats up the air and ocean surface, causing water molecules to evaporate. Evaporation occurs when a liquid molecule of water escapes into the air as a gas. This scientific visualization shows how water evaporation, indicated in turquoise, is driven by the energy of the sun. Notice how the rate of evaporation pulses over land. It speeds up in the day and almost disappears at night. Over the ocean, evaporation appears to remain constant, both day and night. Water in the air in gas form is known as water vapor. The molecule is now fresh water, having left the ocean salt and other particles behind.
The water evaporates and goes into the atmosphere, and then it doesn't necessarily just turn around and fall as rain or snow.
Condensation is the process by which water vapor molecules cool, stick together, and become liquid again in cloud formation. This often happens high in the atmosphere, where the temperature is much lower than it is near the surface.
What happens in the atmosphere is, just like we have currents in the ocean, we have winds in the atmosphere that actually, to some extent, drive what goes on in the ocean currents. Materials in the atmosphere can travel actually a great distance, sometimes, a quarter of a way around the world, until they get to the point where they actually turn into rain or snow and thereby fall back to the ocean or fall back to the land.
This is called precipitation. If the water molecule falls on land as snow, it may be stored for a very long period of time in a polar ice sheet or mountain glacier, depending on climate conditions.
When rain falls or the snow melts, typically the next place it goes, it infiltrates into the soil. So soil is not a solid, it's not like a rock. There are pore spaces in there, and those can be filled with water. And typically there is a certain amount of water in the soil at all times. If the soil was completely dry, then plants wouldn't be able to grow.
If soil becomes saturated, any additional rainfall will collect in puddles and streams. Soil water that percolates deep enough will help to recharge an aquifer.
An aquifer is any underground geologic formation that stores water. So it's typically either rock with a lot of cracks in it, or it's sandy layer. Sand has a lot of pore space in it, it can store a lot of water.
The water molecule might remain in an aquifer for more than 1 million years. More likely, it would help to replenish a stream, which would feed into lakes and rivers. Eventually, the water molecule will return to where it started, the ocean. People also have a role in the water cycle. By pumping water out of the ground for irrigation, cutting down forests for development, and building roads and other concrete surfaces that lead to runoff, people can have a serious impact on the path a water molecule takes.
The most obvious way that people affect the water cycle are the ways that we control the water after it's fallen on the land surface as rain or melts as snow. But we have put in dams and rivers to hold this water. We also pump the groundwater out and use that. So it's these water resources, we call them, are really us taking a natural part of the water cycle and using it to our benefit.
The water cycle also affects and is affected by climate variations.
The water cycle is one of the ways that we will really feel any changes in climate. So climate changes will feed back to water cycle changes, things like how much precipitation an area receives, the frequency of droughts and floods and this sort of thing.
The water cycle is the adventurous journey that water takes through the oceans, atmosphere, and land, driven by the sun. Improving our understanding of the water cycle and how it is changing will be critical for future decisions related to water management, agriculture, natural resources, and climate change.
Now that you know how the water cycle works, here's an activity you can do to create your very own water cycle.
Now we want to make our very own water cycle in a bag. All we're gonna need is a plastic bag, a small cup of water, and something to write with. Like any water cycle, our water cycle in a bag starts with a body of water. My favorite body of water is the ocean, so I'm gonna draw the ocean. Now what does water do from the ocean? It evaporates. So our first step is going to be evaporation. Where does the water go after it evaporates? It condenses. Condensation is our second step. But where does it condense? It condenses in the clouds. So you want to draw yourself some clouds. After it condenses in the clouds, it precipitates. So precipitation is our next step. It's going to come down from the clouds, precipitating. My favorite type of precipitation is snow, so I'm going to draw some snow. Eventually, it precipitates back down into the water cycle, starting back again. Now we have our 3 steps of the water cycle: evaporation, condensation, and precipitation. Now, of course, this is not a real complete water cycle in a bag just yet. We need to open it up, make some room, and put our little cup of water inside. That little cup of water is going to act like the ocean or our source of water. We seal up our water cycle in a bag. Now, if we put our water cycle in the bag in the closest window, the sun will heat it up and the water will evaporate, condense, and precipitate right back down, making it a full water cycle in a bag.
It's awesome that we can create a miniature water cycle. But that makes me wonder, how do astronauts get water in space without the water cycle?
Hi, I'm NASA astronaut Drew Feustel. Welcome to the International Space Station. On our station, our water recovery system is vital to our mission and our survival. Want to know why and how we recycle and filter our water? Let's go. We use water recovery and filtration because it is expensive to launch resupply missions, and the weight of the water is a problem as well. Think about the weight of a single bucket of water. Can you imagine the weight of water for a month's supply for 6 people on the International Space Station? What about the water for a year or more when we leave low Earth orbit for deeper space missions? That's a lot of water, and bringing it with us is not very efficient. On station, we recycle wastewater to get fresh drinking water. This recovery and filtration process includes our urine, moisture we exhale, and sweat, along with the water we use to bathe and shave. It works like this. When we use the bathroom, urine is collected and pumped to a distillation assembly. The assembly spins, pulling the urine to its walls. The urine is heated to evaporate water from the waste and then condensed in the outer chamber to form distillate. Next, the water is pumped to a tank where it is joined with the water recovered from cabin air created by crew sweat and respiration. Down the line from there, odors and any other contaminants are removed with heat. Then iodine is added for microbial control. Our water is checked often to ensure it meets water quality requirements. It is also monitored closely for bacteria, pollutants, and proper pH. The pH scale ranges from 0 to 14 and is a tool used by scientists to measure the strength of an acid or base. Our water is required to be in the 6.0 to 8.5 range. The end result of the entire process is clean drinking water that we get to enjoy every day. The recycled water on the space station is sterile. There's no odor or bad taste. You've seen that water recycling is critical for long-duration missions, such as here on the space station, and will be for future trips to the Moon or Mars.
Looks like NASA scientists recycle water using filtration. Here's an activity you can do to create your very own water filtration system.
Hi, since it's Earth Day, I have a cool engineering craft that allows us to filter water with minimal materials. Throughout history, engineers have designed many water filtration systems using a combination of physical, chemical, and biological processes to remove contaminants and make water safe for consumption. These systems help prevent waterborne diseases, improve hygiene, and support sustainable living in places where water isn't as clean. So today, we're going to be making a really simple water filter with materials we'll have at home. You'll need a plastic water bottle, a piece of cloth, a rubber band, large rocks, smaller rocks, some sand, and some dirty water to test it out in the end. We're going to start off by pouring a little bit of our sand in. You don't want too much because it'll filter too slow then. That's about good right there. And then we're going to put our small rocks in. And before you do this, you want to make sure you wash your materials a little so you can get easy debris off, like dust and stuff. Okay, and now we have our small rocks in. Then we're going to put our larger rocks to filter out larger debris or debris. Okay, so here's our simple water filter. We have our sand, our small rocks, and our large rocks. Some stuff you can do to make it more advanced is put more coarse sand above the fine sand, and then also put activated charcoal above the smaller rocks. This will draw out chemicals like chlorine from water sources. Okay, so now we're going to test our filtration system and see how well it works. So here's some pretty dirty water. We got our top layer of probably sticks and dust, and we have our stuff floating in the middle, and then we have our stuff on the bottom. So it's a good test. It'll take a minute. slowly dripping out. If you do this for long enough, you'll have plenty of filtrated water. This is just one way that engineers design water filtration systems in order to filter water to make it clean to drink. That's the end. Thank you for watching, and I hope you enjoy this craft.
Water has so many unique properties, and here's a video introducing you to another two, adhesion and cohesion.
Welcome to NASA Launchpad. I'm your host, Audrey Staples. You might have heard the saying that opposites attract. And you know, that's true in a lot of cases, like in some bad romantic comedy. Or when you bring a pair of magnets close to each other. North and south poles will snap together. But sometimes, like with water, molecules of the same substance attract. Wonder why? You'll get a better picture of why when you get the chance to see water someplace other than Earth. Like on the International Space Station, commonly referred to as the ISS, where water appears to be nearly weightless. Here's Canadian Space Agency astronaut Bob Thirsk on the ISS with a closer look at water and this special property.
The intermolecular forces cause water to be attracted to itself, which is called cohesion. For example, here are two spheres of water. When the spheres are several centimeters apart, there's no attractive forces between them. But when I bring them close enough together to attract, they merge through their attractive forces.
So, you probably already know that water molecules are attracted to other water molecules, and that's called cohesion. Well, these same cohesive forces are responsible for surface tension. Surface tension is the property of a liquid that makes it beat up when it drifts on the surface. Like a leaf, or your skin, or a coin. Water surface tension is pretty strong. You can check it out with an eyedropper of water and a penny. Take a closer look. See what happens when you squeeze the water out onto the penny, one drop at a time. How many drops do you think you can gently squeeze onto the penny before the water spills over the side of the penny? I bet it'll be more than you expected. Surface tension is what allows the water drops to cling together, forming that dome or bulge at the top. You can see that water surface tension is pretty strong. You can also see the cohesion of the water as it stuck to itself. But the water did something else as well. It stuck to the penny too. Why was that? Here's Bob again to explain and to show how it works in space.
Intermolecular forces can also cause water to be attracted to other materials. This is called adhesion. For example, water can stick to a straw. When I move the straw close to the sphere, the water sticks. Water sticks to many other materials as well. Think about all the things on Earth that you see little water drops on. Windows, tree leaves, even your own skin. Let me show you with my hand. The molecules in my skin will pull hard enough to make the water stick. The water tries to find a balance between the cohesion with the water and the adhesion to my hand. Eventually it settles on an unusual shape that fills the space between my fingers. If I continue by adding water, I can eventually build an entire glove of water that will stay fixed to my hand. It sticks to my hand by intermolecular forces. How cool is that?
You know, if it weren't for gravity, subtle forces like surface tension, cohesion, and adhesion might have a lot bigger impact on our everyday lives on Earth. Would we still use bowls, spoons, and cups? Or would we come up with new tools that would make our lives easier? Well, that's something to think about as we plan to explore places like the Moon, Mars, and beyond. That's it for now. I'm Audrey Staples, and we'll catch you next time on NASA Launchpad.
Adhesion and cohesion work together to create another one of water's special properties, capillary action.
Hi, my name is Stanish Felmian, and I'll show you what we'll need for the next experiments. We'll need a piece of paper and a marker to draw a line in, a Sharpie or any black marker will work, a chopstick or a straw to tape to the back, 2 stands to hold it up, a plate with water in it, and for the next experiment, 5 cups with water in alternate cups and that we add color to, and 3 strips of paper towels that we'll put inside the cups. Now to the experiment. Water mostly flows downhill, but it can also go up. That's called capillary action. Don't believe me? How do you think plants get their water from the roots to their leaves? Capillary action. So, we're gonna do 2 experiments to show capillary action. For our first thing, we have a paper towel, a black line, some water here, and supporters. We're gonna drip, and let's watch. Notice how different colors are coming out. That's because some colors are heavier than others. Like the blue is super light and the red is lower. So like this, the red is not going very well. The blue is smoothly going up. So for the second experiment, we're showing, so these 3 cups were filled with red, yellow, and blue. And now when we put the paper towels in, the water went up the paper towel and then down. The blue and yellow went up and down and made green. The yellow and red went up the paper towel and down it and made orange. Thank you for watching.
We've learned about water in its liquid and its gas form, so now it's time to talk about its solid form, ice.
Ice is something we've all seen, whether it's ice on a lake or ice in your glass. All ice shares some special properties, but just what are those properties and what makes ice so different from other solids? To find out, let's turn to some people at NASA who've made a career out of studying ice.
Well, fundamentally, you probably already know what ice is. It's that ice cube that's in your freezer in your cold drink. Ice at its most fundamental is frozen water.
When water hits a certain temperature, which is 32 degrees Fahrenheit or 0 degrees Celsius, it freezes. And here we have an example of this. Here's ice. This ice was liquid water not too long ago, and it reached a certain temperature and it expanded and it froze into this solid block.
Ice is important to our world because it's one of the main parts of the planet that controls our climate, how warm or how cool it is. In the polar areas, so close to the North Pole, close to the South Pole, it's cold year-round, and we find a lot of ice there, and that ice affects what our weather is like here in the United States.
When most solids are heated, they melt into liquids. When a liquid cools down, it freezes into a solid. But water is special because something very different happens when it becomes a solid.
Ice is a really unique solid. A lot of other liquids, as they freeze and form a solid, that solid is heavier and it's dense and it sinks down to the bottom of the liquid. But as you know, your ice cube floats in a glass of water. So when you freeze water to make ice, it's actually less dense than the water, and so it floats right up on the top.
We have a glass of water, just regular room temperature water, and we take ice, which is 32 degrees or below, and if we drop a couple ice cubes in this water, we see that it definitely floats. And we see that it is definitely less dense than the liquid water.
But floating ice is really important for life on Earth too. If frozen water did not float, it would sink to the bottom of a lake or a pond, or even the ocean. The summer sun would melt some of the ice, but not all of it. Every year, more ice would sink to the bottom until the lakes and the rivers filled with ice and became solid. But ice floats in liquid water, so our lakes and oceans don't freeze from the bottom up. Even in cold weather, living things can still live in the liquid water that is under the ice. Water, both liquid and solid, makes our world a special place to live.
Now that we know what makes ice unique, let's learn how ice melting affects our planet.
What causes sea level rise? If you've been to a beach before, you've probably noticed a sort of line where the ocean water meets the land. Of course, ocean water doesn't stay at the same level all the time. Waves and tides cause the level of the water to rise and sink all day long. But we can measure the height of ocean water many times a day and figure out the water's average or typical height. The average height of the ocean in a particular place is called the local sea level. But the ocean covers most of our planet, so it's way too big to measure with just a ruler. NASA measures the average sea level of the whole ocean from space. This measurement is called the global sea level. People have been measuring local sea level at certain locations along the coast for hundreds of years, and NASA has been measuring the global sea level for almost 3 decades. Over this time, scientists have observed that the global sea level has been rising. The ocean is about 7 to 8 inches higher now than it was a century ago. Why? Because Earth is getting warmer. Glaciers and ice sheets are large masses of ice that sit on land. As our planet warms, this ice melts and flows into the ocean. More water in the ocean makes the sea level rise higher. But that's not the only way seas are rising. As Earth warms, the ocean is warming too. Water expands as it gets warmer, so warm water takes up more room in the ocean, making sea levels higher. Rising sea levels can have an impact on how we live, especially in communities near the coasts. NASA and its partners use the JASON satellites to measure global sea level. It takes approximately 10 days for the satellites to complete one measurement. And after they finish one measurement, they start measuring all over again. By keeping an eye on Earth's oceans like this, we can measure how much sea level is rising and how quickly it is happening. Find out more about our planet at NASA Climate Kids.
So ice melting means that sea level rises, right? Well, not exactly. This experiment will demonstrate how different types of ice melting affect sea level rise.
Oh no, global warming is melting the Arctic ice. Not only I am losing my home, but sea levels will rise too.
Our home is disappearing, but does melting floating ice really cause sea level rise?
I always thought that when Arctic ice melts, the sea level goes up. Let's find out.
Many people believe that melting Arctic ice causes sea level rise. But most Arctic ice is sea ice, which is already floating on water. When it melts, the total water volume stays the same. However, the Greenland ice sheet is land-based ice. When it melts, it adds new water to the ocean, causing sea level to rise.
The situation in Antarctic is even more concerning. The West Antarctic ice sheet is also made of land-based ice, and parts of it are already collapsing. When ice shelves break apart, glaciers flow into the ocean more quickly, accelerating the sea level rise. To understand this better,
let's do an experiment!
You will need 2 clear cups or containers, water, ice cubes, a clay to represent land. To demonstrate the difference between melting sea ice and land ice, follow these steps.
First, for the floating ice test, fill a cup halfway with water and add several ice cubes so they float just like Arctic sea ice or Antarctic ice shelves. Mark the initial water level and wait for the ice to melt. When it does, you'll notice that the water level remains the same because floating ice has already displaced its volume.
Next, for the land ice test, place a small platform inside the second cup, ensuring it stays above the water like land. Pour water into the cup, keeping the platform dry, then place ice cubes on top to represent glaciers or ice sheets. Mark the water level and wait for the ice to melt. This time, as the ice melts and drips into the water level rises, showing how melting land ice contributes to sea level to rise.
This experiment shows that melting sea ice doesn't raise sea levels, but melting land ice does, making the Greenland and Antarctic ice sheets crucial to sea level rise. The dangers of climate change are approaching fast.
Now is the time to take action.
Water has many special properties, and whether it's melting or freezing, it affects all life on Earth. Speaking of life on Earth, we'll talk about the biosphere next. Before we hop into the next sphere, let's learn more about the NASA eClips team. Most of the videos seen during this marathon come from NASA eClips. Our team provides educators with videos, activities, and lessons to increase STEM literacy through the lens of NASA. A big part of eClips is our student-produced content. Our Spotlight Challenges encourage students to engage in experimentation and evidence collection, as well as develop their multimedia science communication skills. See other examples of Spotlight videos on our YouTube channel and learn more on our website, nasaeclips.arc.nasa.gov. The biosphere encompasses all life on Earth. Let's dive right in to find out how and why NASA studies the biosphere.
Hey, welcome to NASA Launchpad. I'm your host, Audrey Staples. As we've mentioned before on Launchpad, NASA doesn't just do work in space. The vast majority of NASA's workforce is right here on Earth, and there's a lot of work going on to understand our own planet. Our planet is made up of unique communities known as biomes. How do you determine what makes up a biome? Well, for the answer, let's head out to Arizona and check out the amazing structure that is Biosphere 2. B2, as it's known, is currently operated for environmental research by the University of Arizona. So let's hear about biomes from Matt Adamson, Biosphere 2's Program Coordinator for Education and Outreach.
So a biome is a major geographical region on Earth that contains its own unique or distinctive sets of plant and animal life. So you have things like savannas, oceans, deserts, tropical rainforests. All of these would be considered major geographic regions with their own unique plant and animal life. Inside Biosphere 2, the biomes we have are all either tropical or subtropical in nature. And so we have things like a tropical rainforest, a savanna, which is a grassland, a coastal fog desert, and we do have our own saltwater ocean.
Ecologists use patterns of climate, looking at factors like temperature and precipitation, as well as the kinds of plants or animals that live in an area to divide the world into different biomes. And although every kind of biome on Earth is not represented in this amazing structure, each biome and Biosphere 2 is based on an actual biome here on Earth, complete with smaller ecosystems. And the biomes inside Biosphere 2 make it an ideal place for research. But what exactly is being studied? I'll let Matt explain.
There is a fundamental question that connects terrestrial ecology to global climate change, and we want to study the sensitivity of key terrestrial biomes as they relate to variability in global climate change. By running both drought and warming experiments in this controlled ecosystem, we expect to gain a more mechanistic understanding of the future response of tropical rainforests to climate change from the individual plant level all the way up to the level of an entire ecosystem.
Okay, we know that all living things are closely related to their environment. Any change in one part of that environment can cause a ripple effect throughout the other parts. And B2 uses biomes in the world to learn about those ripples. But why rainforest, especially the largest one in the world, the Amazon rainforest in South America?
So the Amazon is of interest because it's one of these key sensitive terrestrial biomes I mentioned, in that it contains unparalleled biological diversity, it contains a globally significant store of organic carbon, and it is a potent engine that drives the water and climate cycle on Earth.
I understand why the University of Arizona wants to learn more about biological diversity, or the variety of life found here on Earth. But how does NASA fit into all of this?
So our significant rainforest research really is connected to two key legacies of the large-scale biosphere-atmosphere experiment in Amazonia that was funded in large part by NASA. So essentially what that means is we're taking data that NASA has already paid for through other projects and using it to compare to responses in our rainforest here, which is in a controlled setting, so that when we're changing things like gases in the atmosphere, temperature, reducing precipitation when we put them through droughts, we then can compare this sort of controlled data to real-world data that NASA's collected through these, for example, these flux towers that are collecting data throughout the Amazon. So sort of a synthesis of real-world data collection and controlled world data collection.
Talk about having a great setup to change an independent variable, observe the results, or dependent variable, and compare those results to real-world data. I guess those aren't just words in your textbook. Now, what about a specific example of this research?
One that is underway and has been for some time is a study of volatile organic compounds in the atmosphere of the rainforest biome. And volatile organic compounds essentially are the 1% of our atmosphere. If you consider that 78% of our atmosphere is nitrogen, 21% is oxygen, the remaining 1% or less are things that we would think of as greenhouse gases, carbon dioxide, ethanol, things like that. And the person who's studying VOCs in our rainforest is particularly interested in the natural production of ethanol in rainforest systems. So we're actually collecting gas samples from the rainforest and then analyzing them in his lab. He hopes to get a baseline understanding of natural production of ethanol, because if we think about moving to ethanol as an alternative energy source, so as we power automobiles, for example, with ethanol instead of gasoline, well, it could be that we're substituting one greenhouse gas, CO2, for another in ethanol. And so he wants to understand some of the natural occurring ethanol before we as human beings perhaps start putting a lot of industrial produced ethanol into the atmosphere. So that's one example of how we're using our rainforest to study natural processes, and in this case, an analog to the Amazon.
It just goes to show you, the scientific process is never complete. Scientists are continually making observations, collecting data, predicting results, and analyzing their findings. That's it for now. I'm Audrey Staples. Thanks for watching, and we'll catch you next time on NASA Launchpad.
Another way that NASA studies the biosphere is by zooming way out. Let's learn how NASA uses satellites and data to better understand how our Earth supports life.
3, 2, 1, 0.
When you think of NASA, you probably think of this. But as soon as we made it beyond the limits of our atmosphere, one of the first things we did was turn our cameras around and look at this. The first U.S. satellite was launched in 1958. That's 11 years before Neil Armstrong became the first person to walk on the moon. Explorer 1, built at the Jet Propulsion Laboratory, initiated a long legacy of satellites meant to take our understanding of Earth to new heights. In 1997, NASA launched a satellite that began a 20-year continuous global record of the very thing that, as far as we know, makes Earth special: life. While most satellite missions capture data on the physical characteristics of our planet's climate and weather, others allow us to measure life itself. The result? The most complete view of global biology to date.
The greatness of this data set is kind of hard to explain. It allowed me to understand ocean in such an organic way.
That's the voice of oceanographer Dr. Ivona Setinik. Ivona and the rest of the NASA Goddard Ocean Ecology Lab help oversee the 20-year dataset. If you take a closer look at this animation, you'll see what looks like a repetitious ebb and flow on the land and surface of the ocean. We're actually watching the planet breathe.
About half of the total photosynthesis on the planet occurs on land and half in the oceans.
That's Dr. Compton Tucker, who pioneered satellite monitoring of vegetation on land. The spring and summer months kick off the growing season for plants on land, illustrated in dark green, and tiny microscopic plant-like organisms in the ocean called phytoplankton, seen in the light blue. They take carbon dioxide out of the atmosphere and use it for energy, causing the total amount of carbon in the air to drastically drop. The opposite is true during colder months. During winter in the northern hemisphere, which is home to most of Earth's land plants, carbon in the atmosphere increases as plants go dormant. And then there are extreme zones in the ocean. Purple patches are nearly devoid of any phytoplankton. They're basically deserts at sea, while the red zones tell us that there's either a high concentration of phytoplankton hugging the coastline, or our satellite sensors are picking up on another input changing the color of the water.
We have a marvelous biological diversity of plants and animals, both on the land and also in the oceans.
But hold on. If we have an amazing biological diversity of plants and animals, why do scientists spend all of their time observing plants?
You know how they say you are what you eat? In the same way, if we want to understand the ocean and life in the ocean, we have to start from the base. If phytoplankton is changing, the whole ecosystem will change.
The changes that Ivona is talking about are much easier to see when we can study a continuous global record. And that means not only being able to look into the past, but also into the future.
It's this long-term data set allows us not only to see exactly what's happening, but to be able so much better way to predict what's going to happen.
A global perspective gives scientists the power to forecast events like harmful algal blooms, disease outbreaks, and even famine. Maybe one of the most useful applications of the data is its ability to show us where we've been. In 20 years, the planet has changed in noticeable ways, and this dataset gives us a visualization to prove it. Arctic greening coupled with retreating Arctic sea ice are probably one of the most well-known examples of this.
If you look at the higher northern latitudes, you see in the white where there's snow, and that then moves further north and recedes. It's then followed by very, very green colors because plants are really photosynthesizing in those dark green periods.
Scientists think that there are likely trillions of planets, yet Earth is still the only planet we know of with life. And with that in mind, our habitable homeworld seems ever more fragile and beautiful when considering the vastness of unlivable space.
I have several friends and acquaintances who are astronauts. They all say the same thing. When they're in orbit, on the space shuttle or in the International Space Station and look down at the Earth, they see one climate, one planet. We're all in this together, and we need to work together to make sure that life as we know it continues on this wonderful planet.
Now that we understand the big picture, let's focus on my personal favorite season, winter. How do organisms survive, and how do we study it? Learn more with this NASA eClips video.
Well, Globey, I think I'm properly prepared for what lies ahead. I guess you could say this coat is my adaptation for cold weather. What is an adaptation? Asked my trusty companion. An adaptation is a structure, maybe a part of the body, or a behavior, like putting on a coat, that helps a living thing survive in its environment. Some adaptations help living things meet their needs. Others keep them safe. Still others help living things live in different climates. And believe me, I'm gonna need this adaptation where we're headed. We're gonna study winter, the history of winter. Once a year since 2001, NASA Goddard Space Flight Center helps host the History of Winter program in Lake Placid, New York. Lake Placid is in the Adirondack Mountains in New York. This area gets more snowfall than any other region in the state. That makes it a really good place to study winter. Well, you might be wondering, why would NASA want to study winter? Well, because learning about what lies beneath the snow and ice helps us learn about what's occurring in our world. An important part of NASA involves studying Earth. NASA is very interested in what's happening both on and around our home planet. Looking into a snow and ice biome allows scientists to study plants and animals that live there. A biome is the area where certain plants and animals live. Winter biomes can be really harsh, so the plants and animals that live there may need some special adaptations to survive. Let's hear more from an expert.
Well, it's a different challenge during winter for all species to live and survive and find their way of making a living. So in the snow biomes, it gives us a different perspective on how difficult and how important those critical adaptations are, where they have to deal in a big way of their lives in areas where there's snow and ice and cold a good portion of the year.
So what kind of life can you find in the snow?
Some of the animals who live above the snow on a regular basis are caribou, Arctic hare, and then some of the animals that take advantage of living under the snow are things like Arctic brown squirrels, all the little invertebrates. Meadow voles are perfect at living under the snow. Some birds like ptarmigan and grouse, they'll nestle themselves in the top of snowpack and actually stay in there for many days and ride out a blizzard. So there are a lot of animals who, on a regular basis, do very well living through the winter in snowpack.
So some of the adaptations these animals use help them find shelter. What other adaptations might you see in a winter biome? Do these animals have to do what I did and pull out their winter coats?
Some of the animals like canids, the dog species, wolves and fox, they put on extra coat. They have an insulating long hair and they're very well adapted to the winter. Little invertebrates and frogs create a chemical and can withstand freezing solid, and they won't rupture their cells because they have kind of like an antifreeze that we use in our cars to keep the cells from rupturing.
Frogs have a type of internal antifreeze? How about that? What are some other adaptive wonders of nature?
Some important adaptations, for example, in snowshoe hare, is they have very large feet. It's almost like they have snowshoes on. It gives them a little bit extra ability to be on top of the snow.
So now we know some of the ways animals adapt to the cold, but I bet with a little more research, you could find more cool adaptations. But how do scientists go about studying all of this? They build a snow pit.
In order to study some of the different properties of snow, we can dig the nice smooth surface straight down so that you can see it's actually a record of the entire winter from top to bottom. And the top would be the most recent snowfalls, and the bottom would be the very start of winter when the first snowfall fell. You might not be able to see every day, but it gives you a week by week or event by event record of the entire winter.
So what can we learn from studying these snow pits?
If you look at a snow pit, you have a whole record of what happened through the winter. And that gives you some idea of how the animals that live at the bottom can take advantage of that structure of snow. Snow pits are good not only to understand how snow falls and what the record is, but also to see how animals who live within that snowpack can make it through the winter.
Wow, Globey, NASA's History of Winter program is awesome, and anyone can get involved. Just go to the History of Winter website. Right there. Just one more question. Next year, can I come?
So, animals survive the winter by using their adaptations, but how about plants? Here's a spotlight video to clear up the misconception that plants die in the winter.
Hey Tanner, man, I can't believe surfing season's over. Bummed.
Dude, nah, Brody. Don't reside in the negative, man. We still got some tubular memories.
Totally, we shred some killer waves. Yeah, at least we have all these nice plants to look at to next year.
Yeah, wait. Dude. Don't plants die in the winter, though?
Yo, no way. I never thought about that, though. Ah, man, you put me back in the negative.
Hey guys,
Why the long faces?
Hey man, we're just sad that all the plants are gonna die in the winter.
Well, I believe that's a misconception, guys. Don't you know that plants don't die each winter?
They don't?
Of course not. You see, boys, if a plant actually did grow during the winter, you'd see the bright leaves and colors that you see in the summer. But the water in the trunk, stems, and leaves would freeze, causing lots of damage to the plants.
Then don't plants freeze and die in the winter and then grow back in the spring?
No, not at all. When the temperature drops, the plant's metabolism slows down, and it even slows photosynthesis, which means that the plant's growth stops. By doing this, the plant goes into a dormant state and is prevented from freezing. It's almost like a bear in hibernation.
Isn't that the same as the plant just dying? I mean, looks dead to me.
That is wrong too. Even if the plant looks dead from the outside, it can still be alive. Many plants have roots underground that are still somewhat active, and like a hibernating animal, can continue its normal life in spring.
Oh, so plants are still alive in the winter, but they just slow down growth and go dormant?
Exactly.
Wait, what? Dude, plants don't die in the winter. Really? Oh. You should have paid attention to that darn.
Man, that summer learning loss is real.
Let's learn more about plant life, starting with photosynthesis.
Hi everybody, I'm Lily, and this is Our World. What do you think of my new plant? I just got some seeds to grow more just like it. You see, I'm getting ready to join one of NASA's engineering design challenges. I'm going to design and build a plant growth chamber like the astronauts might use. I want to make sure my seeds grow, so I've got a lot to learn. I know that a plant is a living thing, just like people. And just like people, it has specific needs in order to survive. But a plant does things very differently than people. So I need to know more about plants before I can design my chamber. My teacher, Mrs. Jones, helped me set up a video chat with Dr. Gregory Goins. He's a research scientist at NASA's Kennedy Space Center, and he knows a lot about plants. I hope he'll be able to help me learn how to take care of mine. Oh, there he is now. Hello, Dr. Goins. I'm Lily.
Mrs. Jones said you would be coming by. What can I help you with?
I'm trying to grow some plants, and I want to make sure I take care of all of their needs so they can grow big and beautiful. Mrs. Jones said that light is a very important need for plants.
It sure is.
I'm planning on growing my plants inside. Is that going to be a problem?
Well, tell me what you know about light.
Well, Mrs. Jones taught us that light travels in waves, and visible light has many colors called a spectrum. But I'm not sure why plants need light.
Plants need light as an energy source to power the food-making process.
Wait, plants make their own food? How do they do that?
It's a metabolic process called photosynthesis that happens in the green parts of the plant.
Photosynthesis? What's that?
You'll get a clue if you break the word apart. Photo means light, and synthesis means making food. During photosynthesis, molecules of carbon dioxide and water are restructured into sugar, and this reshuffling requires energy.
So the energy is the light from the sun?
Exactly. Light is absorbed by a special pigment in the plant called chlorophyll. It's the molecule that makes plant leaves green.
Huh. I'm not green, so I guess that means people don't have chlorophyll inside them. And I can't make my own food, so plants must be a really important part of my food chain.
That's right. Photosynthesis is central to life on Earth as we know it. Everything animals eat has come from the photosynthetic process.
So if light is so important to plants, what do I need to think about if I grow my plants indoors?
When growing plants indoors, there are two factors to consider: the quality of the light and the quantity of the light.
What do you mean, quality of light?
You learn that the spectrum of sunlight has many colors in it. Plants require mostly red and blue light to grow well. Artificial light, such as the light from light bulbs, doesn't usually have all the colors of the spectrum, and plants don't tend to grow very well under it.
So is there a better way for me to get light to my plants indoors than regular light bulbs?
Yes, fluorescent bulbs, such as this one, have a much better balance of the spectrum, and they grow plants very well.
And what about the quantity of light?
That refers to the brightness of light. Direct sunlight usually has more than enough quantity and the correct quality to successfully grow plants.
What if I put my plants right in front of a large window?
As long as your plants get direct sunlight. All plants are different, so you'll need to find out how much light your plants need.
I guess I'll need to do some tests and figure that out. Oh, one more question. Why does NASA study plant growth?
With astronauts staying in space longer and eventually going to other planets and beyond, they would need to grow their own food. But on a spacecraft, there aren't any big windows, and even if there were, you would have only 45 minutes of daylight every 90 minutes while orbiting the Earth.
But if they don't have enough time to get light from the sun, how will the plants grow?
One lighting system that holds a lot of promise is light-emitting diodes, and they last a very long time. They also emit a very narrow part of the spectrum, pure red or pure blue.
Those are the colors that plants like best. But wouldn't these lights affect the way the plants look?
Remember that plants don't use the green part of the spectrum. They reflect green light more than any other color while absorbing the red and blue light. Therefore, when grown under red and blue light, they absorb 100% of the available light and appear black.
Black plants? That wouldn't be very pretty. I wonder if other colors of light would change the way a plant grows, or the way they look. I'd better hit the books and find out the best way to get light to my plants. Thanks, Dr. Goins. Whew, that's a lot of reading, but now I know a lot more about taking care of plants. Let me tell you what I've learned. In order to make food, plants need to carry out photosynthesis. That takes place in the leaves of the plant. And in order to do photosynthesis, the leaves need water, carbon dioxide, and sunlight. The chlorophyll in the leaves traps the energy of the sunlight, and the water comes up through the roots. Then the leaves get carbon dioxide from the air, through tiny pores or holes on the undersides of the leaves. The plant uses the trapped sunlight to turn the water and carbon dioxide into oxygen and glucose, a special kind of sugar. Plants use the glucose for energy. Another thing I found out about plants is that they can move. Not like you or me, of course. That would be scary. But they can react to a change in their environment or stimulus. These reactions are called tropisms. For example, a plant will grow toward its source of light, or it will grow its roots toward a source of water. And the roots of most plants grow downward, the same direction as the pull of gravity. How do you think plants would grow in a reduced gravity environment like the International Space Station? Would I need to change my design for a plant growth chamber if it went to space? Well, I have a lot of designing to do, so I need to get working. After all, NASA's waiting. And if you'd like to join one of NASA's engineering design challenges, just check out the NASA website at www.nasa.gov and search for design challenges. I'll see you next time on Our World. Hey Mom, I need some adult supervision.
If plants make their own food through photosynthesis, I wonder what else they can do. Here's an experiment you can try to prove that plants can move.
Hi, Isha. Scout and I are on a walk. Isn't nature beautiful?
It is. I wish I could take my pet plant for a walk, but he can't even move.
That's actually a common misconception. Plants move all the time. It's just really hard to see. Plants move in response to light, water, and gravity.
Really? How can you tell plants move?
We first need to understand how plants work in order to understand why they move. So let's take a closer look.
Plants can often be influenced by sunlight or water nearby, drawing them to move towards the source. These processes are respectively known as phototropism and hydrotropism.
Put a houseplant on a stable surface near a window. If it was already near a window, rotate and move the plant so it appears it is leaning away.
Put toothpicks near the large stems to help you determine if your plant is moving.
Tape a piece of paper to the window. On the houseplant, mark the leaf tip closest to the window.
Using a ruler, measure the plant's distance from the window to the marked leaf tip. Record your measurement.
The point where the leaf touches the paper can also be marked. Write the date and time next to these marks so you can trace the leaf's path. Measure your plant's movements every hour or every day. Also check the toothpicks you placed as movement markers.
I now understand how plants work. I think I'm going to start a plant journal of my own.
We hope that you learned a little bit more about plants today and how they interact with their environment. We encourage you to explore the plants near you and monitor how they move over time.
That brings us to the end of the biosphere. We learned how NASA studies life on Earth and took a deep dive into the life of plants. Next, we'll be looking up at the atmosphere. Before we hop into the next sphere, let's learn more about the NASA eClips team. Most of the videos seen during this marathon come from NASA eClips. Our team provides educators with videos, activities, and lessons to increase STEM literacy through the lens of NASA. A big part of eClips is our student-produced content. Our Spotlight Challenges encourage students to engage in experimentation and evidence collection, as well as develop their multimedia science communication skills. See other examples of Spotlight videos on our YouTube channel and learn more on our website, nasaeclips.arc.nasa.gov. The final sphere that we'll be covering is the atmosphere. The atmosphere is made up of all of the gases that surround us and our planet. To kick off, let's learn about the composition of our atmosphere.
For thousands of years, the magical dragon of knowledge has been teaching those in need. He has worked with scientists throughout the ages, but the question still remains, who will the dragon help next?
Oh, hey, Tony.
Hey, Alex. Aren't you glad it's finally warmed up around here? The air feels so nice. I'm so glad it's mostly oxygen.
Actually, that's a common misconception. The atmosphere isn't actually mostly oxygen. It's actually mostly nitrogen. But I see what you mean. Fresh air is refreshing.
Alex, you gotta be kidding me. The air has to be mostly oxygen, or else we wouldn't be alive right now.
Come on, Tony. It's not that hard to wrap your head around. The atmosphere is mostly nitrogen.
Man, I really wish there was some mythical creature that could explain this all to me.
Whoa! It's the magical dragon of knowledge.
Well, Tony, your friend Alex is correct. The Earth's atmosphere is 78% nitrogen and only 21% oxygen, with the most of the last 1% of the atmosphere being argon, as well as some water vapor. This means that there is almost 3 times as much nitrogen in the air than there is oxygen.
Wait, then how do we breathe? And why is there so much nitrogen in our atmosphere?
Fortunately, Tony, we don't need that much oxygen, and nitrogen is extremely important too. Nitrogen is actually a pretty important structural component of proteins. The levels of nitrogen in the atmosphere doesn't fluctuate because the nitrogen cycle returns all the nitrogen that's used up back into the atmosphere.
Wow, I was so uneducated. Thank you so much, magical dragon of knowledge.
See, Tony, this is why you need to pay more attention in class and go to more reliable sources, like nasa.gov.
Whoa! Where'd it go?
Bye, magical dragon.
Bye.
I guess, wherever you are.
So, the atmosphere is mostly made up of nitrogen and oxygen. That covers 2 out of 3 of the most important gases for life on Earth. Let's learn more about the third, carbon, in this video.
Pine trees, bumblebees, and Swiss cheese, what do these all have in common? It's carbon. Carbon can be found almost everywhere. Find out just how important carbon is to life on Earth next on Real World. Carbon is not only the 4th most abundant element in the universe, it's also one of the essential building blocks of life. It's in our bodies and in our food. But what is carbon anyway?
Carbon is one of the basic building blocks of life on Earth. It's found all over the place, like in animals, plants, and it's also found in non-living material, like rocks and the atmosphere.
Carbon is important for many reasons, including providing lots of the power that we use. It's found in coal, it's found in fossil fuels, it's found really in all of our main sources of energy. We can find carbon in many different types of source pools. There's a lot of carbon in the ocean. That's actually one of our main carbon pools on our planet. You can find carbon in the atmosphere as different gases, such as carbon dioxide, and you find lots of carbon in the terrestrial areas, so in plants, in trees, or in soils.
So what else do we know about this carbon cycle?
So the carbon cycle is the cycle of where carbon goes, and also how carbon moves from one pool into a different one.
Carbon cycle is a system, this Earth process, that transfers carbon from the plant material to the atmosphere, back to the plant material, from the oceans to the atmosphere, back to the oceans, and from far below ground, from fossilized carbon pools to the atmosphere.
So fast-moving carbon, for example, is what gets stored in plants. You have photosynthesis that happens, which is essentially really a mechanism by which plants are able to absorb carbon from the atmosphere, and they essentially use the carbon to make sugar, which is the basis of all carbohydrates. And that carbon that's fixed there in these plants is fast carbon.
Slower carbon will refer to, over time, sort of the integration of perhaps atmospheric carbon into the ocean and down into the depths of the ocean. One manner in which it's transferred from the atmosphere to the oceans might be through the photosynthesis that's done by plankton in the ocean, and then the consumption of that plankton by higher level species, and then the eventual decay of some of that organic material. Those species will, to some extent, decay and be transferred to the bottom of the ocean, where the carbon that used to be part of those species gets locked away in ocean sediments.
Humans have a huge impact on the carbon cycle because essentially we are changing how it is. We're taking a lot of these pools of slow carbon and burning it and putting it into the atmosphere. So we're really changing where the carbon is, and that has some big implications. So we're not really changing how much carbon is there. The amount of carbon is always the same, but what we're changing is where it is and what form it's in. So if you put the carbon, take the slow carbon, you burn it, and you put it in the atmosphere, it gets expanded, and the atmosphere is a much smaller pool than the ocean is, for example, or our terrestrial reservoirs are.
Humans have a really important role in the carbon cycle. But how does NASA measure carbon as it moves?
We have different ways of measuring carbon. For example, we work on measuring the carbon that's stored in trees. And to do that, we use different types of instruments. We do field work, and we also use satellite data. For example, data from some new satellites like ICET-2 and JEDI.
One way we do those measurements is with satellite imagery or satellite estimates. We use LiDAR instruments that are in space that are pointed down at the Earth, that shoot LiDAR pulses towards the Earth and measure the time that it takes for those pulses to return to the satellite sensor. From those pieces of information, we can learn about the height of forests and other structural characteristics of the forest canopies.
In addition to using the satellite data, we also have to do field work. We go in the field and we measure what species it is. We get the biometry of a tree, which is a biometry is measuring of the living things. We take a tape and we put it around the tree and we measure the circumference, measure the height of a tree, and then we compare that to what we're getting from the satellite.
We would like to get a better understanding of where carbon exists on the landscape.
Carbon really is essential to all life as we know it. And we can see the carbon cycle in motion thanks to NASA's Eyes in the Sky, on the ground, and in space. See you next time on Real World.
Students just like you can help NASA track carbon dioxide in our atmosphere. Let's do an experiment to get a better understanding of just how much temperature is affected by carbon dioxide.
Oh no, it's so hot here. Why is the temperature increasing every year?
I don't know, but I heard CO2 is the cause of it.
I've heard that CO2 doesn't really make a difference in warming the Earth.
I want to understand how much it affects me.
Then let's do an experiment!
This experiment aims to demonstrate the heat-trapping effect of CO2 and clarify its role in climate change. To demonstrate the difference between an atmosphere with increased CO2 and one with a normal air composition, follow these steps.
You will need 2 identical 1.5-liter plastic recycle bottles, silica gel, clay, 2 temperature sensors, CO2 spray, timer, infrared lamp, IR lamp socket and stand, recording sheet.
Silica gel placed inside both plastic bottles to remove any moisture present. Just before starting, the silica gel is removed from both bottles. Next, CO2 is introduced into one of the bottles by injecting it for about 15 seconds using the CO2 spray. Temperature sensors are then inserted into both bottles, which are sealed with stoppers. The bottles are positioned equal distance from the infrared lamp to ensure they receive the same level of exposure.
The temperature sensors are turned on, and the initial temperature readings of both bottles are recorded. Once the infrared lamp is turned on, a timer is started, and temperature readings are taken every minute for a duration of 5 to 10 minutes. Recorded temperature data is plotted on a graph to visualize how the temperature changed in each bottle.
The bottle containing CO2 should show a faster and higher temperature increase compared to the control bottle. This demonstrates that CO2 absorbs and retains infrared radiation, reinforcing its role as a greenhouse gas.
Greenhouse gases like CO2 and methane absorb infrared radiation, trapping heat in the atmosphere. In contrast, nitrogen and oxygen, which make up most of the atmosphere, do not absorb infrared radiation. This experiment simulates this effect, illustrating why increased CO2 contribute to global warming. By demonstrating this concept, you can better understand the impact of human activities on Earth's climate and the importance of reducing CO2 emissions.
It's time to make a change!
The atmosphere has 5 layers: the troposphere, stratosphere, mesosphere, thermosphere, and the exosphere. The troposphere is the one closest to us. It's where planes fly and where you'll find clouds. Speaking of clouds, let's learn more about them.
Ooh, that one looks like a bunny. Or maybe a kangaroo. Oh, hi. Have you ever had fun just looking up at the clouds and seeing what forms they take? Have you ever wondered how they form and why they take different shapes on different days? Well, let's find out.
So what is a cloud?
A cloud is a visible group of water droplets floating in the atmosphere above the surface of the Earth. When billions of water droplets group together, they become visible clouds. I have a friend at the Virginia Air and Space Center who knows a thing or two about clouds. His name is Richard Biles.
Well, hi, Evan. I'm glad you could come to the Virginia Air and Space Center today, and I want to talk to you about clouds and how clouds are formed. Now, clouds are very neat, very necessary for life because clouds give us rain and pure water. Otherwise, we wouldn't have any water to drink or to grow our crops. So clouds form when water in the air moves upwards, and when it moves upwards, it gets lower and lower pressure and expands, and that makes it colder. When it gets colder, then all these little water droplets that are in the air, all the water vapor turns into droplets, and they hang on to small dust particles and other things and become little droplets and reflect white, and we can see them as clouds. All the different kinds of clouds we have are only water vapor in the air. And so our water vapor is very important to us, and when that little ball of water droplet gets big enough, it falls out. And what's that called?
I know. Rain.
That's right, precipitation. It comes out as snowflakes, sleet, hail, snow, or rain. So we're going to make a cloud here by using something very, very cold called liquid nitrogen. Now the liquid nitrogen that I have in here is 196 degrees centigrade or Celsius below zero. For those of you who's still stuck on Fahrenheit, that's 321 degrees below Fahrenheit. So that's so cold. That's so cold that it is going to freeze this water, make vapor, and make a cloud. Now I have the water warmed up here in a wok. Now we're going to make a cloud by using liquid nitrogen, but liquid nitrogen is so cold, before we start we must use our safety gloves to make sure we don't burn ourselves or give ourselves frostbite. Now the liquid nitrogen you cannot see, it is clear. And it's just as clear as water is. I mean, you can see that it's a liquid in there, but when we get ready to pour it in here, what will happen it will boil, because it will turn back into a gas. When it boils, it's going to take that water with it and make water vapor in a cloud. So what you're going to see now is the water vapor coming out and making a really big cloud. So Evan, what do you think about that? We've just made a cloud in the museum.
Wow, you made a cloud? In a wok? That's a homemade cloud.
Okay, Evan, I want to say one more thing. You know that clouds sometimes come down to the ground. Clouds on the ground are called fog. And we can make a fog bank here and see fog being made by pouring the rest of this liquid nitrogen out onto the ground. Here we go. Look at that fog. That's the same cloud that is in the sky, but it's on the ground.
I never thought of fog like that. Fog is just a cloud on the ground.
See you later, Evan. Thanks for coming.
Wow, that was fun. Now let's explore clouds a little more. Clouds can be divided into two general categories, layered and convective. These are named stratus clouds and cumulus clouds. Stratus means layer in Latin. Cumulus means piled up in Latin. These two cloud types are divided into three more groups by their altitude, or how high the cloud is. Clouds can be broken up into three basic altitude groups or categories. Low clouds have bases below 2,000 meters. Middle clouds have bases between 2,000 and 6,000 meters. And high clouds have bases above 6,000 meters. Within the different altitude ranges, a number of different types of clouds can exist. You can think of them as players on a team. Each team member has a different name.
And now, your starting five for the low cloud team. Stratus, Nimbostratus, Cumulus, Stratocumulus, Cumulonimbus, and your sixth man, Fog. And now for your mid-level team, Altocumulus and Altostratus. And the high-level players are Cirrus, Cirrocumulus, Cirrostratus, and Contrails.
Clouds not only come in all those amazing shapes, but they also come in a variety of different colors. The color of a cloud tells us what's going on inside the cloud. Clouds form when warm air containing water vapor is lighter than its surrounding air, and this causes it to rise. As it rises, it cools, and the vapor condenses out of the air as tiny droplets. To condense means to change from a gas or a vapor to a liquid. These tiny droplets of water are packed together so tightly that the sunlight can't penetrate far into the cloud before it is reflected out. This gives a cloud its characteristic white color. Under certain conditions, the droplets may combine to produce larger droplets. Those large droplets may then combine to form droplets large enough to fall as rain. These larger droplets interact differently with light. Here's something for you to think about. Consider how much easier it is to see through a heavy rain than a heavy fog. It has to do with how much light is able to transmit between water droplets. The interaction of light with cloud particles of different sizes and amounts causes the array of shades from white to gray and even black. Other colors can occur naturally in clouds. A blue-gray color is the result of light scattering within the cloud. A greenish color occurs when sunlight is scattered by ice. A cumulonimbus cloud showing a greenish tint is a pretty good predictor of heavy rain. Now you're a cloud expert, so the next time you're lying in the grass identifying shapes in the clouds, call them by their real name.
Now that we know more about the types of clouds and how they form, let's learn how students can help NASA track the clouds in the sky.
Speaking of clouds, I have this really cool, rare, awesome, epic, and not to mention rare cloud cover estimator. This helps me estimate what percentage of the sky is covered by clouds. And did I mention that it is rare?
Thanks, Jacob. Now that version may be rare, but anyone can make their very own cloud cover estimator right at home. Okay, so in order to make my cloud cover estimator, all you need is a plastic covering. So I use this plastic bag, some tape, a pair of scissors, and just a plain marker. My favorite color is purple. So I have this nice box right here that I just cut out the end so that I can see straight through. And I'm going to start building the actual part of my cloud cover estimator. I will take my marker and I will draw 10 grids on this small portion of this Ziploc bag in order to put over my little viewing area. Now, on one end of the box, I will tape the part of the Ziploc bag that I drew, and I will tape that to the end of this box. And on the other side as well. So now I have this cloud cover estimator, and when I'm looking at the clouds in the sky, I can estimate how many clouds are covering the sky based off of how many clouds are within the view of my grids. So for an example, I have 10 grids and I'm looking at the sky, and I only see the clouds covering about 3 out of 10 of my grids. That means only 3 out of 10, or 30% of the sky is covered by clouds. So as you can see, this really nifty tool helps me estimate the coverage of clouds in the sky, or the percentage of the sky that is covered by clouds.
You can use the cloud cover estimator and other tools to submit your scientific observations to globe.gov. Data from students can help NASA better understand their satellite data and how clouds affect our environment. Now, let's move above clouds and beyond the atmosphere to the sun. Learn how NASA uses solar energy while they're in space by watching this video.
Hi, welcome aboard the International Space Station. I'm astronaut Ricky Arnold, and I'm currently at one of our human research facilities on ISS, where you can see centrifuges, laptops, and other scientific equipment. Across from me is another one of these experiment racks, where you can see ultrasound imaging, more laptops, cameras, other equipment, all stuff that requires electrical power. In fact, we have so much equipment for science and life support that our electrical system has about 8 miles or 13 kilometers of wiring to make it all work. So where does this energy come from? Let's have a look. From here in the cupola and through other windows, you can easily see the solar arrays soaking in the sunlight. They are massive. These 4 solar arrays are made of solar cells, which are purified chunks of the element silicon. Together, the solar arrays contain a total of 262,400 solar cells and cover an area of about 27,000 square feet, more than half the area of a football field. That's huge. When the station is in sunlight, the solar arrays produce about 60% more power than we actually need during the daytime. That extra power goes directly to charging our lithium-ion batteries. Now, those batteries are essential because they provide the power we need during the 16 night times we have per day here on the space station. The energy our solar arrays can produce is enough to power 40 homes, and we can maximize the power we generate by rotating the arrays in 2 axes, one like a windmill to track the sun through the course of the day, the other to track the sun's inclination, or its angle in the sky. The space station's electrical power system uses direct current to provide energy for our laptop's lights, water recovery system, and science experiments. Thanks for coming aboard today. Now back to Earth.
Now that we know how NASA scientists do it, here's an activity you can try to harness the power of the sun for art with a solar oven.
Jacob, please show us how to make a solar oven.
Yes, I can. A solar oven will allow us to cook or heat something up with just the energy from the sun. What we're going to need is a dark or black sheet of paper, a plastic drinking straw or some sort of stick, aluminum foil, clear plastic wrap or any sort of clear plastic, some safety scissors, and make sure to be careful when you're using them, some tape, and a box with a lid on it. Now, some boxes already have lids, like shoe boxes and pizza boxes, but not all boxes do. I didn't have a box with a lid, so I had to make one. And what I did is I just taped together the top of a box, and then I cut around the sides with about 1 inch to spare on each side. First, take your dark piece of paper and cut it so that it can fit inside your solar oven. Next, put your foil on the lid of your box, and this is going to reflect the sunlight into the oven. Now take your clear plastic and stretch it across your opening. This is going to keep the hot air inside the oven. We need that lid to stay open so that the sunlight can get in. So tape your plastic straw on your lid. Now that we have our solar oven completed, it's time to put something in the solar oven. You can cook all sorts of things in here. You can cook s'mores, marshmallows, anything you like. I like to make art though, so I'm going to make some melted crayon art with our solar oven. So I took some old crayons and I took some pieces off of the back of them, and I'm putting them on our sheet of paper right here. I'm going to arrange mine in a circle because after it all melts, I kind of want it to look like a new planet. Once you have it on your paper, you're going to open up your solar oven, pick up that plastic, and then you're going to put it in there. And you close it back up. So we want to put our solar oven out in the direct sunlight, and we're going to come back to check up on it every 10 or 15 minutes until the crayons are completely melted. We are back, and I can see that the crayons are completely melted, so now it's time to take them out. Be careful because this does get very, very hot. It can get up to 160 degrees Fahrenheit, so it is very hot. Here we have our completed piece of crayon art, and Sarah, this crayon art is for you.
Visualizing our solar system can be difficult. How can I stand on Earth and understand just how far away the sun and the other planets are? Here's an activity you can do to visualize just how far the planets are from each other while staying on Earth.
It takes forever to walk to the lunchroom. For real, it's like as far away as Mars. Whoa, did you just say that the lunchroom is as far away as Mars?
Yeah, if you think this hallway is long, wait till you hear how far apart the planets really are.
How are we going to do that? Yeah, how far is Mars really? We're going to build a model, but first we need a roll of toilet paper. Toilet paper? What does that have to do with the planets? Well, we are by the bathroom. Sun is right here. Now let's roll. Mercury is nearly 60 million kilometers away, but our model is just 2 squares away from the sun.
Venus is a little farther at 4 squares.
Earth must be next. Yep. Earth is just 5 squares away. In Mars?
8 squares from the sun. That's your long way to lunch.
Oh wow, so Mars really isn't that far compared to the others. Yep. Exactly. Jupiter is way out at 14 squares. And Saturn?
48 squares, that's almost a whole gym.
No way, and the farthest planets? Uranus is 97 squares. And Neptune is 152 squares! Okay, I take it back. Having to walk to the lunchroom was nothing compared to having to walk all the way to Mars. Yeah, I would never say Mars is close again. See, you just need a little space science.
Now let's walk to lunch, Earth distance style.
Thanks Thanks everybody for tuning in to our Earth Day video marathon. Before we hop into the next sphere, let's learn more about the NASA eClips team. Most of the videos seen during this marathon come from NASA eClips. Our team provides educators with videos, activities, and lessons to increase STEM literacy through the lens of NASA. A big part of eClips is our student-produced content. Our Spotlight Challenges encourage students to engage in experimentation and evidence collection, as well as develop their multimedia science communication skills. See other examples of Spotlight videos on our YouTube channel and learn more on our website, nasaeclips.arc.nasa.gov.